It's working. Yay. Okay. Testing 1, 2, 3, 4. Here we are. So say I have two rectangles. All right. Here's a rectangle. Here's a rectangle. Rectangle, and say this rectangle is 5 by 3. And I take a rectangle that is similar to this rectangle, and I make it 3 times as big. Okay? So say I tell you that these are similar in shape. Okay? So if I make it the scale factor is what you multiply to get the other side. So the scale factor in this case, we're going to say that's 3. So if I multiply this side by 3, what do I get? What do I get? 9. And if I multiply this side by 3, I get 15. So if the sides get bigger by 3, how much bigger does the area get? You should be ready. So it gets 9 times as big, right? Right? The area of this was the investigation area, right, is equal to 15. But the area of this is equal to 15 times 9, which is big number, right? 45 times 135, is that right? 49, 45 plus 135, right? So the area of this is 135. So even though you're just multiplying the sides by 3, the area is getting 9 times as big. Or what's another way I can come up with that number of 9? Where does that 9 come from? Where's that 9?
Adding 3 to this side, 3 to this side.
Well, if you think about it, right? If this is 5, right? 5, 5, 5, 1. If I have 5 divisions, go 1, 2, 3, 4, 5 squares this way. Whoops, that's not very good squares. And 3 going this way, I have 15 squares, right? But basically what I'm doing when I'm finding a scale factor of 3, I'm dividing this into 3 more little squares, right? So whatever the side ratio is, whatever the scale factor is, you square that scale factor to find the area, the scale factor of the areas, okay? And this is conjecture. I gave you that conjecture sheet, or all you guys are absent, you got that conjecture sheet? So that's what conjecture C, or S, yes, C96 says, okay? If the corresponding sides of 2 similar polygons or the radii of 2 similar circles are in the ratio m to n, then their areas compare in the ratio m squared to n squared. For example, okay, say I know that, let's do another one, okay? Say I have a circle, right? Is that covered? Oh, here's my circles. Here's a circle, that's not a circle. This is a circle, okay? So here's a circle. Here's a circle. I'm going to move this circle down, okay? So I know that the area is 100 pi, okay? And I know that the area of this is 25 pi. Find the ratio, find the ratio of the areas. So let me write that on there. C96. If sides or radii have the ratio are in ratio m to n, then areas are in ratio m squared to n squared. Okay? So if I know that the ratio of the areas is 100 pi to 25 pi, area big, we'll call this area the big, to area the small. Area the small. What is that reduced to? 4 to 1, right? Is that the ratio of the sides? Is that the ratio of the sides? Or the ratio of the radii? Is that the ratio of the radii? No. That's the ratio of the areas. So if I squared the ratio of the sides, if the sides are in the ratio of m to m, then, and the areas are in the ratio of m squared to n squared, how do I find the ratio of the sides? What's the opposite of squaring something? Square rooting it, okay? So the ratio of the radii is going to be the square root, right? The square root of m squared to n squared, right? So equals m to n. So you would take the square root of 4 over the square root of 1. What's the square root of 4? 2 to 1, right? So even though the area of this is 25 pi and the area of this is 100 pi, the radii only went up, only doubled. What is the radius of this circle? What is the radius of this circle? How would I find the radius of the circle? How would I find the area of a circle? Pi r squared. So what's r? 5. What's r in this case? 10, right? Is the ratio 2 to 1 or 1 to 2?
Yes.
Yeah, see that? Okay, so the ratio is 2 to 1 even though the actual side length is 5 to 10. That's why, you're right, if they say on Domino's, oh look, you could get 2 10-inch diameter pizzas for only $9.99, and you get one 20-inch diameter pizza for $10.99, or say for $15.99, which is a better deal? The bigger pizza, right? Because here you're getting 4 times as much for only $5 more, right? So if you get 2 of these, you'd only be getting twice, right? You know, so when you're figuring out pizza, you know, I used to be in the pizza business, you know. I made a lot of dough. Did I tell you that joke already? Oh, shucks. It's kind of cheesy anyway. All right. So what if I have one? What if I have one that looks like? So going back to, what if I had something like? What if I have a picture that looks like this? Okay. I just made up some nice problems last night. Here's a triangle. Here's a triangle. So this works for any type of similar figure. So I have this kind of triangle here, and this triangle here, and I'm gonna make. What am I gonna do? I'm gonna find the altitude of this triangle. Okay. So here is this, and here is this, and these are altitudes. Okay. And I tell you that these two triangles are similar. And I say that this is 5. And I say that this is, oh, whoops, I meant to say 3, not 5. And that this is 3, that this is 3, and this is 7. And I'm going to call this triangle ABC. And I'm going to call this triangle DEF. And I'm going to tell you that the area of triangle, that's a triangle. Triangle DEF is 98 inches squared. Okay? What is the area of triangle ABC. How could I figure that out? What's the ratio of the sides? What is the ratio of the sides? Ratio of the sides is the same as the ratio of the altitudes. What is that ratio? 3 to 7. So the ratio of the sides, right, is equal to the ratio of the parts. So side 1 to side 2 is 3 to 7, which means that the area of 1 to the area of the 2 is going to be what? What's the ratio of the areas if the sides are 3 to 7? Hello? Yes? James? 9 to 49, right? That is the ratio of the areas, 9 to 49. That's equal to 3 squared over 7 squared. Yes? You understand where I got that from? Yeah? So if I know that the area of the small one to the area of the big one is 9 to 49, and I know that the area of the big one is what? What's the area of the big one? 98. Then the area of the small one is x, or your variable, right? So area of the small is to the area of the big, as is the ratio of their areas. Yes? No? Maybe? So I cross multiply. Does this come out? Does it work out? Did I make up a bad problem? 49. Oh, it works out, doesn't it? What's the area of the small? 49 times the area of the small equals 98 times 9. What do I do to solve that? What do I do to solve that? Come on. How do I get A by itself? Divide both sides by 49. How many times does 49 go into 98? 2. So you get the area of the small is equal to 2 times 9, which is 18. So I don't even need to know what this base is, right? All I need to know is the ratio of their areas. Yeah? You get it? It's a little tricky. What would be this base? How could I find this base? Right. 3 times b divided by 2 equals 18, right? So 3b equals 36, b equals 12, okay? So that's the kind of problems you're going to see in this kind of homework, okay? So, and after this one, what time do we get out? Do you know? 25? So I'm going to give you like 20 minutes to get started on this assignment, then I'm going to talk about the volumes, okay? Because it's kind of the same idea, but in terms of volume. Right? So I'm going to pause here for a station break. Where's my pauser? Pauser. And free. So the next thing talks about volumes, okay? Ratios of volumes and similar figures. So this is section 8.6, I think. 8.6. You guys, you gotta focus here. Oh, I have to unfreeze. Unfreeze. Is it unfrozen? There we go. Okay. So volume ratios and similar figures. Volume ratios and similarity. So if I have I do have these in my gallery. I wonder if I could load my gallery. Where's my gallery? Gallery. I don't see it. Is this a gallery? I don't know. I'm just going to draw a box. Here's a box. It's easier to just draw a box. Here's a box. And this box, let's say this box is 1 by 2 by 3 by 2. And I make a new box that is twice as big. Twice as big. So say these boxes are similar, okay? And I make it twice as big. So what's this side going to be? 2. What's this side going to be? Twice as big. What's that side going to be? Ian, take your headphones out. What's this side going to be? Twice as big. Come on.
7.
Go back to the middle school. Okay. What's this side going to be? 6. What's this side going to be? 4, right? What's the volume of this box? What's the volume of this box? 6, right? 1 times 3 times 2, right? 1 times 3 times 2, which is 6, right? 6, let's say that's inches cubed. What's the volume of this box? Right? 2 times 6 times 4, which is 48. How many times bigger is the volume of this box than the volume? How many times is that? 8 times as big. So I just blew, so my scale factor is 2, okay? But scale factor equals 2, so if the scale factor is 2, what do I do to that 2 to find out the scale factor of the volumes? I cube the scale factor of the volumes of the sides to find the scale factor of the volumes, okay? So right? So that's what C97 says, okay? If the sides for similar figures, if sides are in the ratio S1 to S2, then the volumes are in the ratio S1 cubed to S2 cubed. That's conjecture C97, okay? So if the sides are in the ratio 1 to 2, then the volumes are in the ratio 1 to 8. I keep getting these notifications. So here's an interesting problem. Say I have this figurine, you know figurines? This little guy, okay? The little figure. And say I make him out of some metal or something, and I make this guy 6 inches tall, okay? But in real life, this guy is 6 feet tall, okay? Here he is. He's 6 feet tall, okay? He's 6 feet tall. And they're similar figures. So I make a model of like 6 foot man, okay? But I want to make it real. Okay? And say in real life that the weight of this guy, if I make it out of this, weight, W-E, that's an H. The weight of this guy is half pound, 1/2 pound. So I make this little 6-inch model, okay, and he weighs half pound. How much does the big guy weigh? How much does the 6 foot real or actual, I don't know, the figure weight, okay? Can anyone tell me how I'd figure that out? What's the scale factor? How many times bigger is 6 feet than 6 inches?
Wait, no.
12, right? Because right? 6 inches is half a foot. So if he's 6 foot tall, the scale factor is the ratio of the sides. So side 1 to side 2 is equal to 1 to 12. Do you guys understand that, right? 0.5 feet to 12 to 6 feet is 1 to 12. What's the ratio of the volumes? Volume 1 to volume 2. 1 cubed to 12 cubed, right? Because the dimensions are going in all the directions. Yes? So 12 cubed, I did that on my calculator. That's some big number. Oh, could someone do 12 cubed on their calculator? I didn't actually put it into my calculator. Anyone do that?
1,728.
1,728. So the volumes are in the ratio 1 to 1,728. So since weight is a function of volume, right? Right? If it's made out of the same material, then their volume. So if this guy weighs 1/2 pound, right, as 0.5 is to x, right? So I get that x is equal to 0.5 times 1728. Whoops. 1728. So what's half of 1728? 8 something? 864? 864?
Yeah,
Correct?
yeah.
864. So this guy weighs 864 pounds, you know? So that's like when you're making a model or something. Oh, this guy only weighs like half a pound. This guy weighs 1,700 times as much, even though the dimensions only went up by 12. That's why the Titanic sank.
Exactly.
Seriously though, because when they made the model, oh look, he floats just fine, you know. But then, when they didn't realize when they made the actual, I don't know if this is really why the Titanic sank, but right, the mass increased way more. Like think of this, if this were a person, right? This is why very tall people have a lot of foot and bone problems, because the surface area, and that's why elephants have really big ears. It's true. Because elephants, proportionally, they have way more volume than surface area. How do you cool yourself off if you're an elephant? Well, how do we cool ourselves off?
Flap your ears.
Jump in the swimming pool.
You flap, how do we, yeah, but how do we cool ourselves?
Sweat.
Yeah, you sweat through your surface area, right? Through your skin, right? So elephants proportionally, this is true, elephants proportionally, they have way more mass per unit surface area than we do, right? Because they have way more volume proportionally. That's why they had to evolve to get really big ears so that they could have more surface area to help cool off their bodies. You know, that's why elephants have big ears. And that's why, like, people who are really tall, they'll have a lot of foot problems because if you're really tall, you have a higher proportion of weight to your surface area than a person who's more proportional, and your feet are like, they're more a function of your area, right? So if you're standing on less area per unit of weight, you're gonna hurt your feet more.
Unless you have big feet.
Unless you have really, really big feet, but still, you know, that's why old people like
Side
me
22.
run in Hokas. You know what Hokas are? They're like super cushiony shoes, so that I don't injure myself when I'm. Okay. Anyway, that's kind of. I think is that enough for this lesson to teach you guys? Can you figure it out from there? Hopefully. So with this, so the second part of the homework, I cut it down from what's on that assignment calendar. Just homework page 616. Just 1 through 11, just the odd ones, okay? So that's just, what, 5 problems or something? 1, 3, 5, 7, 9, 6 problems. Okay, so that's not too bad, right?